Okay, so we're going to start with the last talk of the program. So it's a pleasure to introduce Andrei Okounkov, who's my colleague at Columbia University. He's done work in, I'd say, more fields than I have fingers: algebraic geometry, representation theory, probability, integrable systems. I need one more: mathematical physics. And for a combination of these works, he won a Fields Medal in 2006. He's currently on the advisory board for Clay Mathematics Institute, and he's going to regale us on characters and difference equations.
Well, thank you so much, Ivan. I'll begin by saying that I wasn't meant to be speaking in this conference. I'm replacing Terry Tao, who's recovering at the moment, and we all wish him the speediest possible recovery. And I thought, since this is the last talk of the conference, it's also a good time to maybe once again reflect on CMI's many accomplishments in this past 20 years, and just the sheer amount of things they funded is amazing. The impact they had on mathematics, and while I myself benefited from it as a Clay Senior Scholar, but more importantly, I was involved with PCMI, and more importantly with MSRI, an institution that whose support by the Clay Foundation meant a lot, made a great deal to the success of MSRI programs. And in particular, so this, by the combination of this being a spontaneous talk and me making this point about Clay's support of MSRI, I felt like maybe I should talk about not some developed subject, but rather just an idea that came into existence during this past spring. We had a program on enumerative geometry at MSRI. Balish, somewhere here, was one of my fellow co-organizers, and Nakajima was a Clay Senior Scholar. As you see, Nakajima will feature very prominently in this story. So it's, like I said, it's just an idea, but I thought since it's a spontaneous talk, it'd be appropriate to talk about it. And looking at what CMI has accomplished, you'd think, well, maybe there's an army of people behind it, but in fact, it's just an army of two, and we're sure we're all wishing Nick the absolute best with the new direction that his career is taking. I understand it's taking him to very exciting and nice places, and we're very grateful to Naomi for the just gigantic amount of work that she's putting into the functioning of CMI. And come next Monday, there'll be Martin instead of Nick in this photo. I'm sure he'll be equally successful. So this is and this is also. So Nick, thank you so much for everything you've done, and Naomi's not here, but and also this is a good moment to remember some people who are unfortunately not with us now, and but whose generosity, obviously financial generosity, but also generosity with vision and ideas, really shaped many things that obviously. The very existence of Clay Math Institute is owes it to generosity of the Clay family, and somehow, speaking of generosity, I think it's very easy for a research mathematician to perceive himself or herself as the center of the universe, where you focus on your own ideas and you channel the support and the energy you get from the outside, from the society. You kind of just channel it in your own world. But I think it's very important also to be generous with your time and ideas and insights with your students, your colleagues, and the general public. And the Clay Math Institute has also done a tremendous amount of work on disseminating mathematical knowledge and sharing with the public the beauty of mathematics. And I certainly would like to add my congratulations to the many congratulations Sir Roger Penrose received on his dissemination award. And I'm very hopeful that this present day's Ashers, the Asher of of today will be very inspired by the images produced by Jason Miller that we saw yesterday to be this kind of new artistic imaging. Now, so going to the talk itself, this is, like I said, this is just about some small random idea in mathematics, and this is in terms of. So Mina and I have been thinking about various applications, some general theory that we have, and the kind of applications we have in mind is to redo some stuff we did with Okounkov, and I'll explain briefly what it is, but you'll see it's neither here nor there. And so what does it concern? It concerns very classical things like representation of Lie algebras. And so it's very basic. I can explain by just very simple example. If you look at SL2, which is after all a space of 2 by 2 matrices with 0 trace, so this is three-dimensional Lie algebra spanned by these 3 matrices there, and very simple commutation relations. And if the characteristic of the field is not 2, that is a simple Lie algebra and the simplest such. And when we teach representation theory, we very often start with representation of this Lie algebra. This is something that can be done very explicitly, but then already contains some seed of the general ideas that go into the general theory. And hopefully that will also play a similar role today. And so what's the representation of a Lie algebra or associative algebra? Well, you look for solutions of these relations, so the relations we had here, when the commutator of 2 matrices is a multiple of the third. You look for solutions of this equation in matrices, maybe matrices of infinite size. And it's very easy to come up with one such solution, namely you start with, you look at upper triangular matrices. They have a one-dimensional representation. That is to say, you can just look at the vector, which I'll denote lambda by this kind of ket notation. And you look at this vector, and you demand that this is annihilated by f. I guess f was a lower triangular matrix, is the way I defined. It's annihilated by f. It's an eigenvector of h with eigenvalue lambda. So this is why it's denoted lambda. And then you consider just a free module generated by such generator and under the action of E. So if you act on this vector lambda by E, then by the commutation relation, the weight, that is to say the eigenvalue of h, increases by 2. So you get a new vector, and then next time you act by E, you get, so maybe I'll be pointing, so you start, you act, you get something of weight lambda plus 2, you get again lambda plus 4, and so forth. So there will be a free module generated with this generator by the action of E. And then from the commutation relation, you can figure out how f acts on this. And so what f will be doing is, well, this vector will be sending to this with a multiple minus lambda, here minus 2 minus 2 lambda minus 2, and so forth. In general, the case step, you'll have this number. And if the characteristic of my field is not 0, or is 0, and the lambda is not a non-negative integer, then this number is never 0. And then what is easy to see, that whatever vector I have in my module, I can first bring it to this highest weight vector, or the lowest weight vector in this case, maybe called vacuum or something, lowest weight vector. So I can always bring it here, and then I can make any other vector out of it by acting by E. So this will be an irreducible module. However, if you thought that all the however, if still in characteristic 0, if lambda happens to be a non-negative integer, non-positive integer, then there will be a 0 of this polynomial. So if we go sufficiently deep, in fact, if we get to the weight which is minus lambda plus 2, then this matrix element is 0. And so you get, inside of your previously irreducible module, you get a submodule generated by this guy. And this is how you get then the quotient. So this part will be a finite dimensional module of, this in fact, so this is something we prove in undergraduate or maybe beginning graduate representation theory, that this is in fact this complete classification of reducible modules for SLT. And so if you look at this, it seems, well, how can this be complicated mathematics? But in fact, if you ask the same question for a more general Lie algebra, then it gets really into deep waters. And what was really so simple here is every one of these H eigenspaces was just one-dimensional. So I could just denote vector by its weight. And so in particular, if there was a chance for some vector to be annihilated by f, we could have chosen this. We knew what that vector was. Whereas, of course, if you look at a corresponding module over high-dimensional Lie algebra, this will be a subspace of some dimension, and this vector annihilated by the lowering operators, what's called singular vectors. They have some room to hide, and it's generally very hard to sort this out. And this is one of the highest achievements of the 20th century representation theory. In fact, to sort exactly this question. If I take such a module over a general finite-dimensional Lie algebra G, well, say semi-simple Lie algebra G, then how exactly it's going to break up into irreducible? That's the subject of Kazhdan-Lustig theory, and it's and a lot of really deep math has gone into that. But now, if you thought the all number theory we're in this conference, we had 4 talks on number theory yesterday, and that was the end. No, so this is I don't know, maybe you'll be relieved or disappointed to see again characteristic P appear. But so if in characteristic P, what happens is that this number here, it can be 0 for 2 reasons, right? It can be 0 because k is 0, and it can be 0 because this bracket is 0. And so then instead of one single submodule in this case, you're going to get an infinite chain of submodules. They repeat periodically mod P. So so you start with the lowest vector. There's something. You go P times from it. You're going to get another singular vector and so forth. And so you get a picture which is an infinite chain of submodules repeating with period P. And correspondingly, the representation, the finite-dimensional representation theory gets a little more interesting. It gets in this, you can get 2 different finite-dimensional modules as a subquotients here, as opposed to just one before. And there is a characteristic P version of Kazhdan-Lustig theory, which is even deeper, and it has 2 kinds of phenomena. One is a phenomenon that may be somehow closer to my interest, is that what happens when P is very large. And there are some very subtle phenomena that happen for, of course, something very difficult is going to happen for very small p's. But something very subtle happens for intermediate P, and this is, well, I have nothing to say about this other than express my deepest admiration for people who advance that theory, and in particular, here we don't have Georgi in person, but here's a picture of Georgi who's been awarded Clay Research Prize for his work in particular on this issue, which really revolutionized our thinking about how this happens. And to quote Andrew from yesterday, I think other committees should really pay closer attention to. So today I'm not gonna talk anything about this kind of what did I say? Transit. Kind of transit phenomena. I'm not going to say anything about them. I have nothing to say, but I will talk about what happens for large characteristics. And so this is right. So the main ingredient in classical Kazhdan-Lustig theory is a certain Hecke algebra, and the Hecke algebra is a deformation of the Weil group, and maybe again I'll illustrate in the simplest example why is this happening? Something has to do with the Weil group. Well, in this example, when we had this finite dimensional quotient in characteristic 0, then the observation would be that the weight of the vector just before the singular one, that's exactly the reflection of your original weight. And the fact that this is, I have no idea what this is. Hopefully not something important. So this is the reflection exactly tells us when this reflection of this vector of this lambda happens to sit in this geometric progression, this is exactly, sorry, this arithmetic progressions of numbers, if minus lambda appears in it, this is exactly when we should expect a finite dimensional quotient. And in general, you should, here instead of the reflection, you should take the Weil group of the corresponding Lie algebra. And what you should really be doing is to replace the relation that the generator squares to 1 by its deformation. This is what's called Hecke algebra. And similarly, it's very easy to imagine that something of the kind must be, it's easy to imagine that something of the kind happening in characteristic P, except now, since previously we were reflecting about the 0, so lambda was going to minus lambda, but now what was 0 before, you should repeat periodically mod P, so it will be a reflection at 0, at P, at 2P, and so forth. And so this reflection will now generate not a group of order 2, but rather a discrete group of discrete reflection group, so that kind of a fine Weil group. Is that clear? And so in general, the way to think about the way Hecke algebra is defined is that you take a reflection group, which may be finite, like the reflections about these 3 hyperplanes here could be unaffine. That's the ones like, for example, take the triangular lattice that we saw in Stas's talk and look at reflections. I mean, if it's really by equilateral triangle, the reflections in the size of these triangles would be a discrete reflection group. And then you can first, maybe it's convenient to look at the Braid group, which is like the Weil group, except you do away with the s square equals 1 relation altogether. So this would be saying that to do it topologically, you take the complexification of this reflecting hyperplane arrangement, you remove the hyperplanes, and then you mod out by the Weil group, then what will happen is that if a path that goes towards the hyperplane and crosses over in positive imaginary, and then going back to another point in the same orbit, this will be, when you go to the quotient, this will be a loop. And so this group will satisfy the Coxeter relation, but not the relations that generator square to 1. And then you can impose further some relations. Okay, for example, you want your square of the generator to be equal to something. That would be, you can get the Hecke algebra this way. And maybe a quick remark on this, still on this transparency, that the easiest thing, if you have an affine hyperplane arrangement, the easiest thing to talk about this, affine hyperplane arrangement, is instead of the hyperplanes in a plane, you take a codimension 1 subtora in a torus, and you do the same thing there, that you're going to get an affine Weil group. And so why am I bringing this up is because a very classical, if you're interested in the representation, if you want the representation of an object like this, and with some relation satisfied. So this is you're looking for representation of pi1 of something, and you impose relations that are, if I go around the loop, then this satisfies some equation. The classical way to get this is to get yourself some flat connection on the space with fixed eigenvalues of the residue as you go around the loop. And so that will, if you fix your eigenvalues of the residue of your connection as you go around the loop, this will fix the equation satisfied by going around the loop. And then the Coxeter type of relation would be satisfied just because they satisfied pi1. And so this is the beginning of some story which I don't want to explain today, but there is some general story that for broad class of algebras that include universal Wellenbeck-Lie algebras and similar algebras, like for example Chernykh algebras, there is a version of mod P Kazhdan-Lustig theory in which the place of the Hecke algebra is replaced by monodromy of a certain natural differential equation. So this is you describe and there's so this is there's some part of this theory is they're theorems now. There's some maybe in some larger context that may be conjectural, but there is some theory. And what I want to describe today has to do with some ideas of how this theory can be made somehow more direct. How can you more directly see? So if I give it like this seems like some kind of deep mathematics, but maybe it is still deep, but it's just maybe you can think about it more in the more concrete terms. So Bezrugalnikov and I, like I said, we've proven some theorems to this effect, and we have more conjectures about the cases we cannot prove. But again, I'm very grateful to Stas not only for getting the factors of 2 correctly, but also for introducing many notions that are oh no, this is not good. So for introducing many notions I'm going to use in my talk, and one of this hypergeometric function. And this he didn't write a formula for it, but this is what it looks like if you denote this this ratio of gamma functions, if you denote it by a bracket like this, and this is just the most natural polynomial of degree k you can think of, which is other than monomial, it's just the product of these linear factors, then sometimes called Pohammer symbol. And so then the series like this has been studied, I guess it was introduced by Gauss as a generalization of many other Taylor series. And maybe the modern point, of course, maybe the easiest way to explain why this is such an important function is a point that I suppose was first made by Riemann, is this function is important because this is the solution of, if you look at Riemann's sphere for differential equations with regular singularities, if there's only 2 such, then you get elementary function. But if you have 3 singular points, then the situation is no longer an elementary function, but still a very nice function, and here it is. So this is the parameters a and b and c have to do with the exponents of your equation. And so this is maybe a more a more geometric way to think about it. So if you think of a second order equation with 3 singular points, the solution would be functions like this. And the reason hypergeometric functions, like for example, the reason hypergeometric functions appear in mathematical physics is precisely the same reason. This is what Stas, I guess he didn't explain this, but if you're studying 4-point correlation in conformal field theory as a function, so you fix 3, and so that would then the 4th point becomes a parameter, and in a minimal model that will of a certain kind that will satisfy as just the operator itself inserted at a variable position satisfies the equation of order 2, and therefore this would be a function satisfying equation of order 2 and growing at most polynomial as you approach 3 singular points, so it has to be a hypergeometric function. And so this is similarly to SL2, the hypergeometric function used to be some kind of appetizer bit for courses that are maybe not have gone completely extinct like Dodo, but are harder and harder to find in catalogs. But now, of course, if there is a good piece of mathematics, it's going to come through the window if you chase it out of the door, because now it's going to come. Now this sort of things come, well, different. This kind of classical hypergeometry and associated Q-difference equations we're going to talk about, they're now entering mathematics as through Peter Schultz's theories and very advanced theories like this, but it's they also have an elementary side to them. So this is what I want to observe about this series, and never mind the numerator. The fact that the numerator of that series factors, that's an accident. It's just an accident of the same kind since there's only one in every power of z, there's just only one term that makes the numerator factor. In general, if you're solving a differential equation, you don't expect the numerators of in the series to factor. There's just no reason for this. But the denominators, this is what we want. This is what we want to focus on. Denominators, what do they look like? What are the structures of the poles there? And this parameter c, you should compare to parameter lambda that we had before. If you look at the kth terms in the series, in characteristic 0, it blows up. You get a pole exactly where we had a singular vector before. And in general, the terms with the pole, they form a progression just like that submodule we had before. And if we look at characteristic p, whatever that means, then it's clear that the poles there'll now be two kinds of poles, namely this number and 0, taking mod p. And so instead of this chain of submodules we previously had, we will have higher and higher ordered poles in this expression. So that in some sense this is the main observation of the lecture. The rest I'll just take it maybe more precise and explains why this happens and what's the generality and this happens. But this is a relation between the world of differential equation and the world of representation theory. So as illustrated by this slide here. And so how do we make this more precise? Is well, actually, how do we? What is the right thing to do is not to talk about k as a number k as having a pole and denominator. The right thing to talk about is talk about Q analogs at root of unity. So this is the proper context of this in this situation, and so this is also kind of comforting for me, because this is my profession is mathematical physics, and I would be very worried if I were somehow have to break into some characteristic P considerations. So I'm obviously not qualified this, but Q analysis root of unity, this is very much inside mathematical physics. And so what are Q analogs? Q analogs is again something that, like I said, is now entering mathematics through this very advanced considerations, but this also has a very long history to them. And so this is you're basically trying to create the theory you previously had for reals and complex viewed as an additive group, replace it by a theory of where you work with the multiplicative group instead. And so that, so in particular, where you previously had arithmetic progressions, you now have a geometric progression with some denominator q, which is just some new variables, just some number in the multiplicative group of your field. And the kind of things like, for example, if you want the reciprocal of the gamma function, well, what would you like? So ordinary reciprocal of the gamma function is an entire function that vanishes at 0, minus 1, minus 2 and satisfies some difference equation. But in the Q world, 0, minus 1, minus 2, this will be replaced by q to the 0, q to the minus 1, q to the minus 2. And if q is absolute value less than 1, we can just write a convergent product that has the zeros. And it satisfies the difference equation, which is direct multiplicative analog of the equation for the gamma function. So for the gamma function, we have this equation. Well, observe here we have an additive shift. So we serve in the additive group, we shift by 1, and out comes the coordinate that vanishes. It is the local coordinate at the additive identity, so this x. And so then, what was the replacement of this equation? Well, we shift multiplicatively by q, and out comes a factor which is a local coordinate at the multiplicative identity. So this is so that would be this would be solution. This is solved. I mean, obviously solves this equation, has exact same feature as the ordinary gamma function does, with the added advantage that it's would. Of course, there are formulas for ordinary gamma functions of this kind, but then you have to regularize this infinite product, where here this infinite product just converges. And so then the analog, so I spoke about how instead of arithmetic progression, we now look at geometric progression with some denominator q. So these are here on my axis here. And but if you're this is like, so to speak, this is for the arguments, but for the values, if you'd like to replace the integers by something meaningful, the best thing to replace them is by if you would like to replace integer n by something, the best thing is to replace it by a geometric progression, the sum of the geometric progression in terms of geometric progression with ratio q. And the best thing is to take it, in fact, symmetrized like this. So, for example, so this function that for so it the so this is the q analog. So 1 is like analog of 0. This is between the 1, 2, and 3, and so forth. So you get 1 root q plus 1 over root q, this q plus 1 over q, and so forth. And the way to think of this geometrically is, for example, you can interpret this as this centered Hodge polynomial for projective space. And maybe this is, you can think of this q being an element in a Cartan torus of SL2, kind of the Hodge SL2, and the way it acts on cohomology of projective spaces, that's the character. And in fact, we're going to, later in the talk, if I get there, we'll be taking some coherent cohomology with some element q acting on it. And that's in fact how this thing happens, how you get q analogs. This is if you think of just really, if this rotation acting on P1, how it's going to act on cohomologies of natural, like O of n on projective space, then you're going to get O with n minus 1, I guess you're going to get something like this. And the point about this Q analog is that satisfy relations which are with expected relations, like this, for example, if Q is 1, this is really n, and if you replace this square brackets with just ordinary brackets, that's clearly an identity, but this is also true with Q analog, in fact true for can write this materic identity. And so now if we go back to this hypergeometric function and just replace, we previously had this bracket defined as a ratio of two gamma functions. Well, but let's take q gamma functions instead. And so this would be this is now redefined to be this product. So it's a ratio of two gamma functions. That the exact same series is known as q hypergeometric function, and this is it's not exactly a new object in mathematics. And the beauty of this object is that it's extremely symmetric. Like for the ordinary hypergeometric function, there's a contiguity relation that say that ordinary hypergeometric function solves a differential equation in the variable z, but it's also second order difference equation in all its variables. Now this object solves a q difference equation in all of its variables, and in fact there's a certain symmetry between the equation that satisfies in Z and the equation that satisfies, for example, in C. So, so this is a very nice object, and so now if we look at this series, now we can, instead of considering situation when we're in prime characteristic, instead we can imagine a situation when Q is the root of unity. Then we have the exact same pattern. So if Q is not the root of unity, then the only pole in this expression happens when C is in the Q's power if lump is an integer, non-positive integer power of Q, and the pole happens exactly where the singular vector was before. And if Q is an mth root of unity, and now we don't have to assume m is prime, it could be anything we want. So if Q is say Q is primitive root of unity, then the poles in this expression are exactly of the kind that you get a first order pole, second order pole, third order pole, and so forth, exactly in the pattern that we had this all along. And so if you want this representation theory equivalent of that, then instead of taking your taking the Lie algebra and considering a characteristic P. Instead, you can take the Q analog of what's called the quantum group. It's an object of a certain history in mathematics. And the main commutation relation there that the commutator on E and F, which was previously H, is now becomes the Q analog of H. So in other words, it's really so there was a certain integrality about eigenvalues of H, and so it's okay to have its Q analogs. This is also everything's going to be defined over a field that maybe contains square root of Q, and so then the picture is that everything's like before. You have these are eigenvalues of H, and the Ex really starting with an eigenvector which has eigenvalue lambda. But then for F, we'll have the matrix element of the lowering operator, F, was exactly the Q analog of the product we had before. And now we observe that this it kills. We have a singular vector precisely in the same pattern as we have we have the poles here on the previous slide. And also in the same pattern as we have in prime characteristic, and that's a general phenomenon. This is there are many. There's a subject of a lot of work by starting with Lustig and continued with very important contribution by many people, including Anderson, Janssen, Zergel, Bezrukovnik, and other people. It's a big subject to prove that indeed this is for large roots of unity, you get the same behavior as in prime characteristic. Large prime characteristic. And so this is maybe the main idea of the talk is that Verma modules over quantum groups. These all modules are called Verma modules, and Verma modules over quantum groups, and more general algebras. So much more general algebras like you take Chernykh. I mean, there are many algebras of the kind I'll explain. They break up, this Verma module break up exactly in the shape that the solutions of certain Q difference equations, they break up. All right, so the rest of the lecture is my explanation why this seems like a correct idea to me. And so this will be something about something completely different. So if you're so this is now comes to what I the things I really actually do. And but then of course before we get there, we will talk about like somehow general. We'll talk about some general ideas and well. So if you have a quantum mechanical system or a random process, then means you have something which just has finitely many degrees of freedom, and then a time. And then one space-time has one dimension. Then the central problem and there is of course to find the spectrum of your revolution operator. You can call it Hamiltonian or something like that. Okay. If you cannot find the exact spectrum, maybe the next best thing is to maybe at least know what the lowest energy state is, because that at least will tell you. This will tell you what would be like if if you have a random process, what will be its steady state, because that eventually all the fluctuations will die, and then you know what the steady state is. And if you have this lowest energy state could be a vector, or could be a subspace, and of course you expect the latter if you have a symmetry group. So in general, you have a group of symmetry that will act on eigenspaces, in particular on the lowest eigenspace, and so this will be some non-trivial representation of your symmetry group. So that's a reasonable question to ask. Now, again, this might be a difficult question, But so this is you can ask an easier question if your evolution operator if your dynamics is supersymmetric. Supersymmetric means you have a square root of evolution operator. There's something like a Dirac operator that squares squares to your operator. And then, and this an operator, you have your spaces Z mod 2 graded, the operator takes even to odd and odd to even, and squares to your evolution operator. Then you may not know exactly the lowest energy state separately in even and odd, but if you ask for the index, that is to say, the difference of these two spaces as a virtual representation of your symmetry group, so if you have a virtual representation, it's a difference of two actual representations. Like, for example, a character of that is a difference of characters. Then this is easier because this object is invariant under deformation. So this is, you may not know exactly the kernel and co-kernel, but you know the index. So that's an easy question to ask. And so this is, we started in this transparency, we started with a reasonably hard question. We made it easier and easier, and now we'll make it hard again by saying that we're really interested in quantum field theory or random fields. Like in Stas's talk, there was something that had two space-time directions. So this is, but at least on this level of discussion, quantum field theory or random field, you can treat as like quantum mechanics on an infinite dimensional configuration space. So this requires a certain discussion, but it can be mathematically defined in this setting. It's not an issue. I'm just explaining what is it we're going to do. We're going to take some. So that's the kind of question I want to ask. And how we're going to. So how we're going to do this is so if you have say a random process such as like molecules of air in this room, they bump each other on very small distances, on nanometers, something. But the steady states in infinite volume are the other name for them is a vacuum of your theory, something that can extend some state of your system that can extend in infinite spatial extent and indefinitely in time. Something. But that's this form a certain this typically form a finite dimensional manifold. Like for example, for gas. This is just has the two coordinates, just the temperature and the pressure. But now, if you're in a concrete room like this, or in a finite box, any finite box, which I have a picture on transparency, what you will have is, of course, the temperature and the pressure will vary slightly from point to point. So you have what you really have like a modulated vacuum, in which parameters change from point to point. Now, you have a map from your physical space to some moduli of vacuum. In other words, this is a fancy, for gas, we'll be saying, all I'm saying is that you have a pressure and temperature as functions of coordinates. But in general, this is the, this moduli space of vacuum could be an interesting, it is an interesting algebraic variety for the kinds of theory I have in mind. And since indices are invariant under deformations, if we want to compute an index in some theory, we might as well approximate it to a theory. So you see, we're computing something which is deformation invariant. Like for example, if you want to compute something happening in a box of a certain size, it doesn't matter if the box is of a size 1 meter or with the size of the galaxy. However, if it is of a size of a galaxy, then it's better approximated by this modulated vacuum picture. So in other words, the index will be the same in your original theory and a theory of maps to your moduli space. Okay? And then now with supersymmetry, we're not interested in arbitrary physical theory, we have supersymmetry. And the supersymmetry means that this, as the physicist says, sigma model is also symmetric, and the amount of supersymmetry we want here, it makes this target space makes it holomorphic symplectic. And so this is we're interested in 2 + 1 spatial dimensions. So our space is a Riemann surface, and that Riemann surface we think of as a complex manifold, and the map be holomorphic. That the condition that this map is supersymmetric. Okay. So we go from so this is, so we make a step that cuts down this infinite, we end up with the theory of holomorphic maps from some Riemann surface to some maybe singular algebraic variety. But this is already good, because at least as you bound the degree, this is a finite dimensional manifold. It means finite dimensional algebraic variety. If you take all degrees, somehow this gets infinite dimensional, but that's fine. Yeah. And so what we would like to say is we would like to now compute something like the index of Dirac operator on this moduli space. And this is, of course, moduli space of holomorphic maps from a Riemann surface to even a smooth algebraic variety. That's already singular by itself. But the fact is also singular. That's, of course, a very singular space. But in algebraic geometry, people do construct something like, by it's a singular variety, people construct what would be, there's the following construction of what should be called the index of Dirac operator. Namely, there is a class in a coherent sheaf, class in K-theory of coherent sheaf that replaces the A-roof genus of this manifold. And then all you do is then just take the Euler characteristic of that, and that's the index of your operator. And everything's constructed in a covariant fashion. So this Euler characteristic of that coherent sheaf is representation of your group, and so this is the index. And the only trace of infinite dimensionality that's left in this approach is that, of course, you have to keep track of the degree. So if you introduce new variables, so you have to sum up over all degrees, and so introduce new variables that keep track of the degree. So you write some new variables z to the degree to keep track of contribution of a degree of a map. And so it's difficult to construct this mathematically, but this has all been done, and this is all solid math. And the central role is the subject. So there may be a general principle which I'm not sure whom to attribute, but surely well known to many people here in Oxford, I imagine, that if you want to do something on a general Riemann manifold or general manifold, in some sense you're done as long as you can do it on a flat space, but fully covariantly with respect to the group of automorphism. And so what is it in this case is that if I just want to study maps from just flat C, or flat, the metric has no point, just standard, just complex plane, I study maps to X, but do it equivariantly with respect, well, I want the equivariance with respect to, this was part of what we wanted to do. We wanted the equivariance with respect to automorphism's fact, but we also bring the equivariance with respect to automorphisms of the base, and this is the only reductive part there is just rotation, so we might as well do just with respect to rotations. And so now we have now this becomes a function. So we sum overall degrees, z to the degree, then you compute the Euler characteristic, you compute this virtual index of Dirac operator on maps of degree d here, and we computed an equivariant K theory with respect to the action of this rotation here, and for the analog of this rotation in the source is maybe the maximal torus of automorphisms group in the target. And the only catch is that this is, of course, a very non-compact space, and so this instead of being well-defined in integral K theory, this is well-defined in some localized K theory, and so this comes out to be a rational function of this variable. So this is a series exactly of the kind that this Q hypergeometric series we saw. This is going to be in fact, well, convergence series is Z, but it's not being this is in which the terms are rational functions of some parameters, including a parameter Q. So this Q will be for this Q difference equation, and what this meaning of Q is in this theory is that Q is an element of automorphisms of an element in my ground field that acts by automorphisms of the affine plane. And before I move on, this is the poles in this expression under excellent geometric control, because they all come from non-compactness, but there is a very nice equivalent compactification. You can just read off all the poles from there and not going to talk about it. There's an excellent geometric control of all the poles in this, how exactly the poles in this expression happens if you. So this is a function. In other words, this is an Euler characteristic of some coherent sheaf on some non-compact space, but exact location of its poles, exact nature of its poles is under excellent geometric control. And there's been a lot of work on this sort of things, and this is maybe, I'm not going to summarize it by saying, but I will. I'm not try to summarize it, but what you should maybe take away from this slide is that all of these functions are like modern day analogs of what Q hypergeometric function was to mathematics in 19th century. That these guys are hopefully are to mathematics in the 21st century. They're a solution of remarkable Q difference equation, where Q is what was rotating the source, and as X, you can take many different targets. If you take something from the algebraic geometry point of view, the simplest holomorphic symplectic variety you can imagine would be like a cotangent to projective space, or even maybe cotangent to projective line. And if you take something like this, you just find these classical hypergeometric functions, and they're analogs of them when instead of having two terms in the numerator, two terms in the denominator, you can have n of those. It's also considered classical hypergeometry. And but if you really new examples have started with some many more exciting targets, like for example, if you take the Hilbert scheme of surfaces, then you get really interesting functions. And maybe to say briefly that the origin of this difference equation, they're of kind of roughly the same nature as Hecke algebras themselves, except there is one conceptual difference, and then they come from some hyperplane arrangement that is not symmetric. It can have some symmetry, but it's only have translational symmetry, but in general no reflectional symmetry. There's no requirement that some symmetry group be acting on this hyperplane on Okounkov in a transitive way. It's just some much more general data. Otherwise, it's kind of like Hecke algebra. So maybe I'll skip this slide. And so then, what would be standing there? So this is I'm explaining what sort of functions one looks at and what sort of different. Well, I didn't explain what kind of difference equation that this thing satisfied, but I just flashed a picture that somehow stands in my mind for this difference equation. But what would be replacing the Lie algebra? And so in this line of work, you deal with holomorphic symplectic varieties, and one kind of important thing one can do with holomorphic symplectic variety, you can quantize it. That is to say, if you have a holomorphic symplectic form, then you have a Poisson bracket in the sheaf of functions, and you can look for a non-commutative deformation of that sheaf of functions, and you can take global sections, and you're going to get the global section of that deformation. That will be a very, very nice non-commutative algebra, which is of the kind that includes and generalizes universal developing of Lie algebra, and many people here, like Toby and Kevin, were somewhere here. Yeah, they study. I mean, this is really their point of view on what's the best way to treat algebras like this. But what I want to say, this transparency is that this is the right thing to do, but not with Eck itself. There's a certain duality which generalizes Langland's duality on this axis, and what you should be quantizing. So the algebra for which Vermeer module will be breaking up is not the quantization of X, but rather the quantization of a certain Langland's dual. of x. And part of this lengthless duality is that the difference equations for the two are the same, but but the meaning is different. What was like a variable z for one becomes an equivalent variable for the other. What was z for in one instance becomes c in the other, and vice versa. So, but the commonality of the difference equation, that's one of the hallmark of this thing. Somehow generalizes the fact that if you take Lie algebra and Lens dual, they share the same Weil group. So this is generalized to the fact that if you have a certain x and it's Lens dual, they have that same difference equation. So so this is how this duality appears, and so I want to have a few minutes to talk about it. Is maybe a core question in all this line research is what to do if a map hits a singularity. And this is in general cannot be avoided. And what does it mean? It hits a singularity. It means the terms in which we were trying to explain the large-scale behavior of the system are become insufficient. There are some degrees of freedom that continue somehow fluctuates, and for us, in a way that, like my friend physicist says, at the singularity, nature comes back to the atomic scale, and you need to somehow you cannot be done with just large-scale degrees of freedom. You need some description of what are the extra degrees of freedom you lose. And this extra degrees of freedom, this means there are some operators you can insert at once you hit the singularity. And this extra degrees of freedom, what they physically mean, this means that there is the picture that you should have in mind that at this point, your moduli space doesn't end. There's a different irreducible component, different branches, physicists would say, that tells you what happens if you insert more and more of this missing degrees of freedom. In some integral, you can put some insertions. If you put many such insertions, or to say if your defect somehow condenses, as physicists would say, then you're going on a different reducible component. So in other words, the coordinates on a different reducible component of your modular vacuum should act as operators in the theory of maps to X. That is the picture that should happen. So means the singularity comes with a different branch that tells you what is happening there at the singularity. So, and this is when Nakajima comes, and I already alluded the importance of how much everybody at the SMSRI program appreciated him being there as Clay Senior Scholar, is that distilling these physical ideas of how that's supposed to happen, Nakajima came up with the construction of this dual as a certain algebra that acts on something called critical K-theory. And critical K-theory, it's a different kind of K-group you can associate to this moduli space for the reason that this moduli space may be written, at least locally, in this case, in fact, globally, as a critical locus. And then for anything that can be written as a critical locus, there's a nice category that replaces its category of sheaves, and the K-group of that category is the critical K-theory. And this is where Nakajima made this algebra X check act. And there's many related works. I don't have time to go into discussing that. But that's the key idea. And the basic compatibility. So this for those of you in the business, what we were doing on the previous transparency, or on one of the previous transparency, we're doing some Donaldson-Thomas type problem, but it's everybody who heard me speak about knows what's coming next. It isn't. So this means I'm for 55 minutes of my talk So this is, I have to wrap up. So then it's maybe 59 minutes. So this is, okay. So then this is, there's a certain, you can study kind of Calabi-Yau type problems in Donaldson-Thomas theory, or you can study more general problems. And we were previously studying more general problems, and this is Calabi-Yau. So in particular, in place of all of my current parameters, in this theory, I have to restrict to just the Calabi-Yau situation. And once you do this, all the complexity we had before, that all goes and it all washes out. This very complicated rational function, it just becomes an integer. The action is just the rank of that K group. And this is equivalent of saying that we were solving, so maybe this would, I'm very close to the end of my talk. We were solving some interesting Q-difference equation. But that Q-difference equation had a point, like if you're ever, like a point where the numerator exactly cancels the denominator, and you just get monomials. And the Q-difference equation you're going to get at that point is just going to look like Harish-Chandra type equations for characters. We know characters satisfy. So in other words, we know ahead of time that the irreducible character is going to be some solution of this equation just by kind of Harish-Chandra type argument. But which solutions, to know which solution, you have to go to this deformation layer of poles, and then but once you remove these poles, you're going to see, you'll just get the character. And so this is the fact that this is, there'll be some action, and we're computing something interesting, but there's a point where something interesting becomes just a trace. And so then in particular for this algebra, the kind of thing, once we restrict to critical K theory and to Calabi-Yau weights, we just find this Fermat module. And then, but the general geometric consideration then tell us that that Fermat module, because the way Fermat module is going to break up into irreducible, is controlled by this exact same kind of geometry that controls the breakup of the difference equation. And so that's basically the reason. So now I'm 1 minute over time, but I do want to go to the next transparency, which is again to thank the Clay family and the Institute and the people behind the Institute for amazing 20 years and what they did for mathematics and for the connection between mathematics and the society as a whole. So thank you so much.